Hello, this is the second video on honors linear algebra and multivariable calculus. In this video, we're going to talk about functions. So what are functions and what are some of the properties and what are some of the notations and definitions that we're going to use? So first, a definition. Given two non-empty sets A and B, a function or a mapping, these are the two words that we're going to use synonymously, from f from A to B is a rule that assigns to every element of A an element f of A in B. The set A is called the domain of f and is denoted by d sub f, and the set B is called the codomain of f. The range or image of f denoted by r sub f or im of f, image of f, is the set that is given by f of a when a is in A. So the collection of all of the functional values of f. Two functions f and g are called equal if they have the same domain, the same codomain, and also their rules are the same. So let's look at an example. If you look at this function f from r to r defined by f of x equals x squared, and g from r to all the non-negative real numbers given by g of x equals x squared. They have the same domain, they have the same rule, but they do not have the same codomain. So these two functions are actually not the same functions. But pretty much everything else is about these two are the same. The domain is the same, the rule is the same, but the codomains are not the same. If you look at the first one, the domain of the first one and the domain of the second one, they are both real numbers. The range of the first one and the range of the second one, they are both non-negative real numbers. But the codomains are in fact different. So that becomes important when we talk about surjectivity or ontoness. So what is surjective? We say f is surjective if for everything in the codomain there is an element in the domain that is mapped to that element. So for example, if you look at the example above, f is not surjective because f of x equals -1 has no solution. But if you look at the function g is surjective. And again, surjective and onto are the same because f of x equals a when a is a non-negative real number always has a solution. So f of x equals a has a solution x equals root a since a is non-negative. Injective or one-to-one means if f of a1 equals f of a2, then a1 equals a2. So for example, if I look at this function f from r to r given by f of x equals x squared, this is not one-to-one because f of 1 and f of -1 are the same, even though the inputs 1 and -1 are not the same. But if you look at this function from 0 infinity to r, let's call that g, given by g of x equals x squared, this is one-to-one. Because if x squared equals y squared, if you have two elements that are mapped to the same thing, then x and y must be the same. Since the domain is all non-negative numbers. So if you take the square root of both sides, you get x equals y because x and y are non-negative. We say f is bijective if it is injective and surjective. So let me give you an example. Let's say you have a function like this, 1, 2, 3 to pi e7. If you define it this way, f of 1 equals 7, f of 2 equals pi, and f of 3 equals e. This is one-to-one because f of 1 and f of 2 and f of 3, they are all distinct numbers. It is also surjective or onto because pi is f of 2, e is f of 3, and 7 is f of 1. So it is also onto. So this function is in fact a bijection. It is bijective or it is a bijection. The composition of two functions. So if you have two functions f and g, so if you have a function f from a to b and a function from b to c, so in order to be able to compose these two, I would need the image of g, so the image of g to be inside the domain of f, because I want to be able to define f of g of x. This is in the image of g. I would need that to be inside the domain of f in order to be able to evaluate f of g of x, because g of x is in the image of g, so that would have to be in the domain of f so that we can take f of that. And that's how we define the composition. Okay, so next definition is the identity. The function ID, which is called the identity function from a to a, is defined by identity of a is equal to a. So it sends every element to itself. So if I take the identity of real numbers, it takes x and it sends it to x. Identity of the set 1, 2 sends 1 to 1, and it also sends 2 to 2. And the domain and codomain must be the same. Of course, identity function is a bijective function, is bijection. A function f from a to b is called invertible if and only if there is a function g from b to a for which f o g is identity of b and g o f is identity of a. So this is important to make sure that both of these two are satisfied. So f is here and g is here. So if you look at f o g, what do? You take an element of b and you produce an element of another element of b, because if you look at f of g of x, x must be in the domain of g, which is b. G of x must be in a because g goes from b to a, and then f of that must be in b because f goes from a to b. So g o f, we want it to be an identity of b, and f o g, we want it to be an identity of b, and g o f must be an identity of a. Now, if one of them is true, the other one doesn't have to be true. So here is an example. Let's look at this function f from 1, 2, 3 to 1, 2. And I'm going to define it as f of 1 equals 1, f of 2 equals 1, f of 3 equals 2. Okay, so I want to see, is there a function g from 1, 2 to 1, 2, 3 that satisfies f o g of x equals x for all x inside the domain of g, 1, 2. So is there such a function? Well, if there is such a function, then I would need this. I would need f of g of 1 to be 1 and f of g of 2 to be 2. These are the only things that we need. So I can just define g of 1 to be one of the elements that is mapped to 1. So maybe 1 or 2. I could do either of them. So I'm going to just define g of 1 to be 1 and g of 2 to be defined as something that is mapped to 2. So if I look at this one, 3 is mapped to 2 by f. So I can define g of 2 to be 3. So if I define this function, then yes, this function satisfies f o g equals x. So the answer is yes. There is a function g that when you take the composition of f o g, that becomes identity. But is there a function that g o f of x is x? Is that possible? It may not be the same g, it could be a different function. Let's call it h. And this function h goes from 1, 2 to 1, 2, 3. Let's see if there is such a function. So what we need is this. We need h of f of 1 to be 1. We need h of f of 2 to be 2. And we need h of f of 3 to be 3. Because remember that the domain of f is 1, 2, 3. Okay, so what does that mean? F of 1, let's plug f of 1 in here. F of 1 is 1, so we get h of 1 is 1. F of 2 is also 1, so we need h of 1 to be also 2. So that's not possible. So it's not possible for h of 1 to be 1 and 2. So that means no such h exists. So you could have a composition that is identity on one side, but not identity from the other side. Okay, so let's move on to one example. So we'll do a few examples, and then we'll do an important definition and a theorem. So here's an example. The function pi1 from a cross b to a defined by pi1 of a comma b equals a is called the projection onto the first component. So it takes a pair of elements a comma b and it gives you the first component. It just gives you a. That's called the projection onto the first component. Similarly, the function pi I from a1 cross a2 cross an to ai defined by pi I of the n tuple a1 through an equals ai. That one is called the projection onto the ith component. Okay, so here's a definition. This is a very important definition, and then based on that definition, we'll do a couple of examples. Given a function f from a to b and a subset s of a, the image of s under f is the set f of s equals f of s where s is in as. So we take all of the elements of s and we look at the image of all of those elements under f and we create a set. That set is called f of s. The preimage of a subset of b is all of the elements that when you take their image, they go inside T. So let me illustrate that in a diagram. So let's say this is A and this is B. So I take a subset here called S. I take F and I apply F to every single element in here. So if I take an element S here, I get F of S. If I look at all of these elements, that would give me F of capital S. Now if I want to find the preimage, I will have to take some subset here, let's say T, and then I'll have to see what are the elements that are mapped to this. Take all of those elements, that one is called F inverse of T. So everything that is mapped to something inside T. So notice that both of these two, preimage and image, are subsets. One of them is a subset of B, codomain. One of them is a subset of A, domain. Okay, so to illustrate that, let's do two examples. Here is the first example. Let F from A cross B to B be the projection onto the second component. So what does that mean? It means F of A comma B is equal to B. So it gives us the second component. For every B in B, we want to find the preimage of this set. So preimage. F inverse of B. So what is this? This is by definition the set of all elements x comma y in the domain in A cross B such that if I apply F to those elements, I get an element in B. Okay, so let's see why that is the case. Let's remember the definition. F inverse of T is equal to all of the elements in A that if I apply F to those elements, I get an element inside T. So let's go back and look at this illustration that I had here. Everything in the domain that when you apply f, you go inside T. So everything in the domain that when you apply f, you go inside T. Everything in the domain that when you apply f, you go inside T. Our set T is the singleton, the set with one element B. Let's now translate this. So this is x comma y inside A cross B such that, okay, so f of x comma y. We know that f is the projection onto the second component. So that means f of x comma y is y. So y is inside B. But y being inside B means there's just one element inside that singleton. It means y is equal to B. So this is the set x comma y in A cross B such that y is equal to B. So it is all of the elements that the second component is B. The first component could be anything. So it means it is A cross B. So this is the F inverse of B. All of the elements with the second component of B. And that completes the solution of this example. And oftentimes when I complete the solution, I put a score at the end. Okay, so here's the next example. Let f from R2 to R be a mapping defined by f of x comma y equals 2x plus 3y. For every real number b, evaluate and describe f inverse of b. Okay, so let's see what that is. So let's write down the definition again. F inverse of b is equal to all of the points x comma y inside the domain such that f of those points are inside the given set. So that's equal to all of the points x comma y inside R2. I'm just going to write down the definition of f. F is 2x plus 3y. That is inside the set with one element, set containing only b. But if that element is inside a set with one element, it means that element must be exactly b. So it is all of the points x comma y in R2 such that 2x plus 3y is equal to b. But we know what that set is. This is a set. If you write it down in the standard form, you would get y equals negative 2/3 x plus b over 2. So f inverse of b is a line with slope negative 2/3 and y intercept b over 3. Okay, so now that answers the question. They said what happens if you change b? By changing b, we get parallel lines. Because the slope is always going to remain the same. The slope is always negative 2/3. The y-intercept is what is changing. So we get a bunch of parallel lines. If I were to illustrate that, I would get lines with slope negative 2/3. So you get lines like this, perhaps. These are pre-images of singletons for this function. Okay, so next we're going to talk about some properties of preimage, and this would be the last thing we're going to talk about. Okay, properties of preimage. Suppose f from A to B is a function. S is inside A, S is a subset of A, T is a subset of B, and Ti's are subsets of B for every I in I, where I is a non-empty set of indices. Then S is inside F inverse of f of s. So let me first write down what f of s is. So this was f of a, where a is in s. Or it's usually better to use the same letter, just lowercase. And f inverse of t was all of the elements that if you take their image, if you apply f to them, you get something in t. So these were the definitions. So let's start proving the first part, and part B and C are going to be exercises. Part A, we're going to show that S is a subset of F inverse of f of s. So let's start with an element s inside S. In order to show that S, so we need to show S is inside F inverse of something. How do we show something is in F inverse? By definition, this is equivalent to, okay, so what does it mean that something is in this set? It means if I apply f to that, then that would be in t. So it's equivalent to f of s is in, this would be our t. The t is here, t is the inside here, is in f of s. So this is equivalent to this. This is true because S is an element of S. So we know that f of S is in f of capital S by definition of image of a set. And that would mean S is inside F inverse of f of S, because we showed that if something is in S, then it would be in the second one. It would be in F inverse of f of S. So that completes the first part of part A of this theorem. Let's look at the second part. We're going to show that f of f inverse of t is inside t. So let x be in f of f inverse of t. Okay, what does it mean that something is in f of something? It means, so by definition, x is equal to f of a for some a inside f inverse of t. This is by definition of image. So in fact, it may be better to emphasize here what definition I'm using here. So by definition of image, I would get that. Now I have to interpret this. What does it mean that something is in the inverse image? Going back and looking at definition, it means if you apply f to that, you get an element of the set. So by definition of preimage, f of a must be an element of t. But we know that f of a is x. We know x is f of a. This comes exactly from here. So that implies x is in t. So what did we do? We showed that if x is in f of f inverse of t, then x would be in t. So that tells us f of f inverse of t is inside t, is a subset of t. And that completes the proof of the first part of this theorem. So if you want to visualize this to see why these two things are valid, here is the visualization. So here is the set A, here's the set B. So we have the set S. Let's look at the first one. It says if you take f of s and then take f inverse of s, f inverse of f of s, so we take s and then we take f of s. If you look at all of the elements that are mapped to f of s, you can certainly see that all of the s is going to be in that set. But there could be more. There could be some other elements that are also mapped to some elements of f of s. So this would be f inverse of f of s, which is why s is inside that set. Now if you start from an element from a set here, t, if you take f inverse of that, it would be everything that is mapped to t. If you take f of that, it could be a portion of this. It could be something inside t, because there are some elements in t that may not be in the image of f. So if you look at this, this would be f of f inverse of t, which would be inside t. So that's the intuition of why the first part of this theorem is true. The second part of this theorem tells us that f inverse of union is union of f inverse, and the third part tells us that f inverse of intersection is intersection of f inverse. And those two I'm going to leave them as exercises. And that brings me to the end of this video. So I will see you in the next video.